Hello everybody! So today we're going to be covering the topic of metaballs. Metaballs are an isosurface-based rendering method created by Jim Blinn, originally used to visualize DNA for Carl Sagan's TV series Cosmos. Later on it found great uses in CAT and MRI scan data visualizations. So the origin of the name Metaballs actually does not originate from Blinn's paper. He tended to call them Blobby Surfaces. Instead, we got the name from the research labs at Osaka University, who really took to the name Metaballs and kind of popularized the phrase, term. These surfaces are generated from volumetric data and are becoming increasingly popular as a method to represent fluids in real-time systems. This can be seen in things such as smooth particle hydrodynamic simulations, Portal 2 actually, which I have a photo of right here, and OE Cake. You remember that little physics game from the early 2000s. Okay, so as we're trying to visualize a density field, we need to first define a density function. It's going to be d, two parameters, x and y, is equal to, just some function that's attenuated by, I'm just going to say ATT, by distance, dst. And now, to make this work, for multiple particles, we're going to have to create a sum for each point in the simulation space. And then we're going to actually throw in a little constant here. This is going to be the blobbiness parameter. When we're actually implementing this, you can mess around with it and you will quickly understand what it means. Just describes how blobby it's going to be. It's going to be like big, or is it going to be small? And if you make it negative, you can actually create deformations between 2 points, where this will actually cave in, and this other particle won't, this other point won't even be drawn. Okay, so this constant parameter times our density function. And now a point, and this is really the equation. So we're going to use this. And now the point is accepted as being on the surface of one of these metaballs if it's greater than or equal to some threshold t. And now that's it. We're done. We'll be covering what functions we can stick into here during our implementation. So the first thing we're going to want to do here is start up an empty project and include all of our necessary libraries we're going to be using. We need to bring in the default SFML libraries. We're only going to use the ones we need. And then we're also going to make two definitions, preprocessor definitions, stating the width and height of the window. And then we're going to define a metaball radius, a metaball threshold. So this is just what will be considered inside of the metaball versus outside. It's the t value we mentioned in the function just a little bit ago. I then create a distance preprocessor macro. Now, directives are not exactly necessary. If you just want to stick these values or code snippets straight into your code, feel free. It won't change anything. So the first thing I like to do is separate out my update and draw functions. So in the game loop, we can just have those ready to go. Now we're going to create a vector to store all of our points where we place the metaballs. We can just create a vector 2f pointer, and that should be good. Now we are going to create an SF texture and an SF sprite. This is kind of a workaround to something in SFML I'm not 100% stoked on. So we have to transfer the array of pixels to a texture, and then we have to apply that texture to a sprite in order to display it on any kind of render target. For us, it's going to be the render window. It's also worth noting that the pixel array, we do the ×4 because we are also including alpha, so red, green, blue, and alpha channels for each pixel. And now we are creating the render window, or running the initialization command for it. We pass in a video mode, which includes our width and our height for the window, a title, and then we use a bitwise OR with the two styles that we want. We want the title bar, and we want to be able to close the window directly, so we do that. And then I personally limit the frame rate to 15, as this is not a well, it's not meant to be run in real time. These metaballs aren't moving dynamically or anything. These are static, so frame rate isn't so much of an importance. If you decide to follow through and look at my OpenGL code I included in the GitHub repo, you'll see that that's where frame rate will probably matter more. Now we've created the game loop and instantiated an event variable, and then created a loop to poll all events that have happened for this frame. So we're just going to be looking for a closed event and also checking if a key was pressed. And in this case, it's the escape key. And if so, we close the render window, safely exiting the program. Now we will run all updates for that frame. We'll clear the render window, making it viable for a new draw. Then we'll draw to the render window. And finally, we will display the render window. Now we're going to make sure that we free all the memory in our vector for each of the metaballs, since they are pointers. So we'll loop through the whole array, and we will free each metaball. Let's fix this. And now we're going to clear the array. And there we go. And return successful. Now we can finally define both of the functions we declared earlier in the code. First, we're going to begin with update. Copy all this down how it was before. So the first thing we're going to do is work with input. So we will examine the mouse, check if there's a left click, and if there's a left click, we want to add a new point to our Metaballs vector. Let's do this. I'm gonna need to quickly add this Boolean variable. This will just prevent the program from repeating the action, because while the button is pressed, it's going to be true every time. It's going to return true, so it'll just keep placing points as fast as it can, or as fast as it updates. So now we're going to get the position of the mouse with respect to the render window. That's very important. If you forget that, you're going to be getting your position across your monitor, which is more than likely going to be incorrect. Now, we want to make sure that when we click, we're inside of the window. We're not outside of it. So like if you go down and minimize a program, it won't place a metaball way out in the middle of nowhere. There we go. Okay, now we want to push back the mouse position using the new keyword. Now since we're using new, it's good practice to use delete. This will ensure that the deconstructor is run in the object. Now we're going to add a new boolean saying we should update the pixels. This is used to make sure we only update when we absolutely need to update, i.e. when a new metaball is added to the scene. This is where the actual metaball rendering code is going to be, nested inside of these two for loops that iterate through the width and the height of all the pixels in the window. Now we need to find the index of where our R, G, B, and A values are for that pixel. This is done by multiplying the row we're on by the window's width and then adding the X value. And then we multiply by 4 to make sure we're at the correct offset. Now we're going to create two floats, D for distance and then sum. Now for the density equation, we're going to have to iterate through all the metaballs in the vector and create a sum out of that. So first we're going to want to find the distance from the pixel to the metaball. We're going to use my preprocessor directive function here. Now we're going to use that distance in our density function that we'll add to the sum. In this case, I use a very stable exponential function that is more or less what's described in Blend's paper. Now, I choose to use this because it's extremely stable, but feel free to use whatever you want. Try the inverse squared function just to get a feel for how this works. Now we're going to make sure that our sum is within the thresholds. I use two if statements in order to create a kind of a smooth step between different levels of the threshold. It just helps give it an outline around the metaballs, making them a little bit more visually appealing. Then otherwise we just set it to 0, and then down here we set the pixel's color. So we're going to keep this in grayscale. So we multiply the sum by 255. This is because the max value for an unsigned integer is 255. And in this color model, that's what we use. Now finally, you want to make sure that your alpha is 255 as well. You want it to always be visual. You don't want to add transparency. Well, at least I don't want to add transparency. And now we have to update the texture with our array of pixels, and then we have to set our sprite texture to this texture, and finally we are going to set update pixels to false. Okay, now one last thing we got to do is draw the sprite. So let's define our draw function. And we want to call draw on our render window and pass in the sprite. Okay, it looks like we have an error. Let's quickly see what's going on here. Yep, just forgot up the ampersand. Make sure it's passed by reference and not value. We can run it, And boom, we're good. We got it working perfectly. And this is just the basic overview of the method for rendering metaballs, but there are many ways you can use these. As you'll see in my GitHub repo for this project, I also implemented it in GLSL shader language, and that one runs in real time. I suggest looking at it if you want to kind of get a bit more out of this, see something a bit more practical. For this project, I didn't want to get too bogged down with people not understanding GLSL or how these shader programs run on the GPU. I figured it was better to just give the overview of how this rendering method works, because once you kind of understand it, it's very easy to implement in whatever else you want to use it in. Now, this last snippet of code I'm writing is just to update the previous mouse button state so that we are able to ensure only one metaball is placed per click. And we're done! So I hope you enjoyed this content. I know there aren't many videos on YouTube about rendering methods for graphics. I hope to bring more of that kind of content on here in the future. And like, comment, subscribe if you're interested. Cheers!